All right. Yesterday, we have already introduced the comparison test. Okay. Comparison test is if if 0 less than an less than equal to bn, if bn converge, an converge. If an diverge, bn diverge. Okay. For all n. If the series n from 1 to infinity, if the big one converge, then the small one converge. Then n from 1 to infinity, an converge because both are positive. Alright. If I don't have this 0 here, I cannot make that decision because an could go to negative infinity. But if both are positive, then bn is bigger, bn is less than infinity, is a constant, converge to a point. An is smaller than bn, so for sure, if you add all an together, it's less than it goes to a point as well. At least it won't go to infinity. 1 to an. If the small one diverge, bn is even then bigger than the an, so the bigger one diverge. Okay. So yesterday we have a example. What example? I asked you to find out the n from 2 to infinity, n squared minus 1. Okay. As yesterday we did this one, and we tried to use this comparison test. It's not working very well because if you compare it with n squared, and one over n squared converge because it's p series. 1 over n squared minus 1 compare with 1 over n squared. Yes, 1 over n squared converge. Okay, this one converge because p equals to converge. This one converges. However, 1 over n squared minus 1 is greater than 1 over n squared. Even this one converge, you don't know if this one converge or diverge because it's bigger than that series. If it's less, then yes. So we eventually, what we did, we have two methods. We compare it with the 1 over 3/2 power, or we factor it and change that into n plus 1, n minus 1 times n plus 1. We did two methods, okay? So we did two to prove that it converge. Today, we're going to look at another theorem to make it easier. Alright, so theorem is limit comparison. N from 1 to infinity, 1 over n squared plus 1. Alright, I don't think I need to use that, but it's a limit comparison. So suppose that an, bn both are positive, and the limit n goes to infinity, an and bn, this equals a constant L, where L is finite and a positive. Then the two series an and bn either both converge or both diverge. Okay, so either when L is finite and positive, then the series A and B and both converge or both diverge. Okay, it's kind of like you compare those two, you divide it, and take the n to infinity, and it equals L. L is finally positive. Now we look at this one again. We'll look at this one again. 1 over n squared minus 1. Now we'll look at this one. N from 2 to infinity. Even I cannot directly use that comparison test, but now I can compare it with 1 over n squared now. Make sense? So now I can use this one. I can compare this one with m from 2 to infinity 1 over n squared. The reason I can do that, because limit n goes to infinity, 1 over n squared minus 1 over 1 over n squared. So this will equals limit n goes to infinity, n squared over n squared minus 1. Keep changing flip, okay, of n squared over n squared minus 1. And this equals 1. It's positive, and it's positive. It's finite number. It's constant number. Then since n from 2 to infinity 1 over n squared converge, then therefore n from 2 to infinity 1 over n squared minus 1 converge. Okay. That makes the comparison much robust, much wider. You can use you can take the division. You can use a ratio, kind of like a ratio test. Okay, we divide it. If it's less than if it's a constant, then it can both converge, both diverge. You don't have to compare this. Which one is bigger? Which one is smaller? This one is much better because now I don't have to worry anything about. You may ask me, oh, how about this? How about n squared plus 5n plus 1? Like that. How about this? Now you don't have to worry about that anymore because you compare it with 1 over n squared, it's 0. So it goes to 1, right? So it doesn't matter if you're plus 1. Previously we have to worry about the bottom. Is plus 1 or plus 2 or minus 2? Will that be matter? I have to compare that, which one is smaller, which one is bigger. Now you just take the limit. You don't have to worry about if it's bigger, if it's smaller. If you take the ratio, if it goes to 1, then you got both converge, both diverge. All right. Let's look at another example. N from 1 to infinity, n over n squared plus 1. All right, I'll give you 20 seconds to try this by yourself. All right. Now I will ask a student, help me and see if you can tell me the answer. All right. I'm going to call a student here. 之间. Could you please tell me if this one converge or diverge? You press the button when you ask a question. Okay. Can anyone tell me if this one converge or diverge? Diverge. Why?
Well, you can compare it with 1 over n.
Very good, perfect. You can compare it with 1 over n. That's perfect answer. So we can compare this one with 1 over n because they have a difference power 1, right? You can compare that. So let's look at limit n goes to infinity. N over n squared plus 1 divided by 1 over n. We got limit n goes to infinity. N squared plus 1 n squared, because keep changing, flip n times n squared. Now this equals 1. Okay, you can use L'Hopital's rule. It's easy to tell is 1 equals 1. And then since n from 1 to infinity, this is a constant, a positive constant, 1 over n diverge, because this is p series, p equals 1. Alright, so thus we have n from 1 to infinity, n squared plus 1 diverges. Perfect. Alright, so more example. Okay, so m equal 1 to infinity, 5, 4 to power n plus 1. I'll give it 10 seconds. Alright, I'm going to ask a student here, see if you think it diverge or converge. Alright, Taylor, what do you think this one?
I think that would diverge.
It would diverge. You compare this one with which series?
It almost looks like a geometric series, so 5/4 would be greater than 1.
But I don't have an n here. I don't have an n on the top.
I'm not too sure then.
Then I can change it a little bit. You can take the 5 out. It doesn't matter. It does not change really a lot of things. You can take the 5 out. How about now? So we can compare. Could you please tell me which series do you think I can compare with?
One over 4 to the power n.
1 over 4 to the power n. This one for sure converge because this is the geometric series. 1 over 4 to the power n. Ratio is 1/4. Make sense? Okay. So now we can compare limit n goes to infinity. 5, 4 to the power n plus 1 over 1 to the power 4 to the power n. Then we got limit n goes to infinity. 4m plus 1, 5 times 4 to power m. Okay, so we can divide everything by, you can use L'Hopital's rule. You can use L'Hopital's rule. We got 5 ln 4n, ln 4n. Derivative of 1 is 0. L'Hopital's rule. If you don't use L'Hopital's rule, it's very easy. Like you can estimate. Okay, that should be the same. 4 to power and dominate everything else. So they cancel it out. You got this is a 5. Alright, so both will diverge or converge. Since we know that the series m from 1 to infinity, 1 to 4m, this converge because r equals 1/4. Okay, this is 1 over 4 to the power n. Alright, so r equals 1 over 4 and less than 1, bigger than 0. Therefore, m from 1 to infinity, 5 to the power 5 divided by 4n. This one also converges. Alright, so more example. How about the series n from 1 to infinity, 1 over square root of n squared plus 1. 20 seconds. Alright, I'm going to call a student here to help me with it. Lacey, do you think this one converge or diverge?
I think it's converges.
You compare this series with which series?
1 over
1 over
root n squared.
root n squared. Root n squared can just say it's just the n, because square root of n squared is n. Okay, we can compare these two. Let's see. Limit n goes to infinity. 1 over n squared plus 1 divided by 1 over n. So you got limit n goes to infinity. N over n squared plus 1. You may think, oh, do I use the L'Hopital's rule? You don't have to. Question? Yeah, Lacey, what do you think? Alright, does this make sense? Before we study the L'Hopital's rule, whenever we have this power thing, what do? We can just divide everything by the highest power. Divide the top by n, you got 1. Divide the bottom by n, actually divide by square root of n squared. Divide this by square root of n squared is 1. Divide this by square root of n squared is 1 of n squared. Okay. You can just quick estimate this is the first power. Square root of square is first power. The constant really does not change anything. Okay, so this n goes to infinity, this goes to 0, it's 1. Alright. If in the test or if you do your math problem, it's just up to you. You would like to use L'Hopital's rule, or you want to divide everything by the highest power. You also get a 1. Since 1 from n to infinity, n diverge, then this diverge. Thank you very much, Lacey. Very good. Now you got it right. 1 over square root of n squared plus 1. This one also diverges. So now you can tell that this comparison test is much simpler than the previous one of compare which one is bigger, which one is smaller. Okay, this is much used more more widely and is more robust. Okay, so example. From 1 to infinity, 2 to the power m plus 1, 5 to the power m plus 1. How about this one? I'll give you 10 seconds more. 10 more seconds, okay? Okay, so I'm gonna call a student help me here. Matthew, could you please tell me which series did you have compared with?
Well, I compared it to the, like, from the n from 1 to infinity of 2/5 to the n. That's what I compared it to. And since r is less than 1, then the series converges.
Okay, perfect. So limit n goes to infinity. We compare the whole thing. 2n plus 1 divided 5n plus 1. You divide this one by 2n over 5n. Okay, you compare with this one. So then we find the limit. N goes to infinity. You multiply up is 5n plus 1, 2n plus 1 times 5n. Keep changing flip. Okay, so you got this one is limit n goes to infinity. 10 to the power n plus 5 to the power n. 10 to the power n plus 2 to the power n. You can divide everything by 10 to the power n. So the limit n goes to infinity. 1 plus 5 divided by 10 is 5 over 10 to the power n. This goes to 0 because n goes to infinity. 1 plus 2 over 10, divide everything by 10 to the power n. This goes to 0 when n goes to infinity. So equals 1. Alright. Since 2 to the power n, 5 to the power n is a geometric series, okay, r equals 2/5 less than 1 bigger than 0, converge. Okay, then the series we have n from 1 to infinity, 2 to the power n plus 1, 5 to the power n plus 1 converges. Alright, so this is pretty simple, right? Alright, so I think after 2 more examples we can move on. 5 n from 1 to infinity, 2n squared minus 1, 3n to the power 5 plus 2n minus 1. So now you look at this kind of series, you don't have to find out which one is compared smaller, which one is bigger. It's much simpler for you to just find out a series to divide with. I'll give you 10 seconds to finish it. The 2n squared minus 1 divided by 3n to the power 5 plus 2n minus 1. Alright, so I'll call student to tell me what you got. Okay, I'll call student here. Travis, What did you got?
I wasn't sure with this one. Would you compare it with 2n squared over 3n to the 5th plus 2n?
Let's compare with the easy one. This is n squared, this is n fifth. What's the difference of the power?
3.
Yeah, we just compare with the 1 over n cubed. Can you tell me if this is serious, if this one diverge or converge? 1 over n cubed, Travis? Does this one converge or diverge?
It would converge.
Because?
P is 3.
Yes, okay, p is bigger than 1, so it converge. So what do we need to do next? We just need to find n goes to infinity. 2n to the power 5 2n squared minus 1 divided by 3n5 plus 2n minus 1 divided by 1 over n cubed, which you can keep changing flip. You put it on the top, so it's 2n squared times n cubed is 2n power 5 minus 1 times n cubed is n cubed, and then you have 3n to the power 5 plus 2m minus 1. That's the reason why I say it's much simpler for us, because all of this 2m minus 1 doesn't really change anything. Okay, so it does not really affect the n goes to infinity. It's just coefficient of the n to the power 5. So Travis, could you please tell me what's the infinity of this one? What do you think this goes? Let me give you more detail. 2 minus n, no. 1. Divide everything by n to the power 5.
It'd just be 2/3.
Yes. So if you divide everything by n to the power 5, everything else goes to 0 except the n to the power 5 exists. This is 2, this is a 3, but this goes to 0, this goes to 0, this goes to 0 because n goes to infinity. So just a 2/3. And this is a constant, bigger than 0. It's a constant. So now we have the same convergence. And n goes from 1 to infinity, 1 over n cubed converge. Very good, Travis, thank you very much. Since p equals 3, then we have the same, we have the series n from 1 to infinity, 2n squared minus 1, 3n to the power 5 plus 2n minus 1 also converges. Okay, alright, so next one, n from 1 to infinity, 2n over 3n minus 2. Okay. Five seconds. Tell me if it converge or diverge. Alright, I'm going to call student here. Jasper, what do you think? It converge or diverge?
It diverges.
Because?
If you compare it with 2/3, which diverges.
Compare with 2/3. Well, you mean, okay, yeah, you can use a comparison test, compare with like this.
Yeah,
And since this one diverge,
right.
okay, it's good, it diverge, yeah. You can compare this with this one, or we can just simply look at the nth term. N goes to infinity itself. 2n over 3n minus 2 equals 2/3. Nth term tests are not equal 0. So it diverge. Okay. So previous one, if you see this, nth term test, it goes to 0. Okay. But n-term test does not guarantee you converge, but it guarantees you diverge if it's not equal 0. Alright, so this is number 6. You can compare it with 2/3. This one diverge. Okay, compare with this one as well. Let me ask you another one. M from 1 to infinity, 5 over m plus square root of n squared plus 4. Does it converge or diverge? Give you 20 seconds. Okay, so I'll call student to help me here. Luke, could you please tell me if this one diverge or converge? Well, which series did you compare with?
Could you compare it with 1 over 2n?
1 over 2n. Very good. So, limit n goes to infinity. 5 over m plus square root of n squared plus 4. Compare with 1 over 2n. So you got limit n goes to infinity. And 5 times 2n is 10n. n plus square root of n squared plus 4. So what did you get the limit for this one?
Limit is going to be 5.
It's be 5. Very good. You can divide everything by n. So basically divide everything by n. You got 10. You got 1 plus square root of 1 plus 4 over n squared. So this goes to 0. So 1 plus square root of 1 is 1. 10 plus 10 divided by 2 is 5. Very good. So this is the constant. But can you tell me the 1 over 2 and does this one converge or diverge?
It's going to diverge.
Because
You can take out 1/2 and then 1 over n diverges.
very good. 1 over n diverge because
Because if the p is 1.
yeah, p is 1. Whenever p is bigger than equal to 1, it diverge. P series only converge when p is less than 1. Okay, p equals 1 diverge. You can use the integral test to get an ln n. It's got ln infinity, so it diverge. Alright, so this diverge. Then we have the series n from 1 to infinity. 5m plus square root of n squared plus 4 diverge. Everyone, this is pretty straightforward, right? Pretty simple. I think you should be able to do a lot of problems. You should be able to finish a lot of your homework for sure. It's just that you find out a simple series, which you can use p series or geometric series directly tell if it diverge or converge. You just take the limit, divide it. If the other one diverge, the previous one, the complicated one diverge. So it's very straightforward, very simple. All right. So I think we can move on to 9.5 and alternating series. Now I'm going to write down a series. 1 minus 1/2 plus 1/4 minus 1/8 plus 1/, let me think, 1/16. Okay. Alright. So now I would like to ask a question, ask a student, tell me here what do you see from, what kind of thing do you see from here? Bella, could you please tell me what you see from this series?
Well, the A is an A to or AN, right? So then the N is in the denominator, and it alternates from. Or no, sorry. It goes, the denominator goes up by 2 and it alternates negative to positive.
Very good, perfect. The terms. First thing is the terms alternate in sign. Okay, in sign. Okay, you can see it's negative, positive, negative, positive. It's alternating in sign. Okay. Then second thing is very good. You say that is a alternating geometric series. Okay. Geometric series with gamma equals geometric series with r with the ratio r equals -1/2. Okay. Previously we have 1/2. Now it's -1/2. Because 1 times -1/2 gives -1/2. -1/2 times -1/2 is positive 1/4. Positive 1/4 times -1/2 gives -1/8. Question? Okay. Alright, so previously we got m from 1 to infinity, 1 over n. This one diverge because p equals 1. P series p equals 1, or your integral test, you got this one diverge. Alright. Now, my question is, what about m from 1 to infinity, -1 to the power n, 1 over n? You can tell the difference, right? It's -1 times 1 over n is alternating series. The previous one, this series is, if you put this one, m from 1 to infinity, 1 over n, this is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. You continue like that. Now, I would like to ask you if this one diverge or converge. I'll give you 20 seconds to try it by yourself. So what you got? Okay. You got to converge or diverge? Okay, I can tell the answer converge. Yeah, it converges. Alright. So before I tell you how to do this, let's look at a theorem. Okay, let's look at a theorem 9.14. Okay, it's alternating series. Let an is bigger than 0. The alternating series -1 to power n an and n from 1 to infinity -power 1 to n plus 1 an converges. Well, this means n plus 1 and the power does not really change, but as long as the sign alternate with each other. The first one positive, negative, or the first one negative, positive, it doesn't matter too much, okay? But it has to be alternating series. Converges if the following two conditions are met. First one, limit n goes to infinity, an equals 0. The nth term test, that's the first condition, okay? Second, an plus 1 less than equal to an for all n. Okay. Just not the signs, not with the signs, but just the an terms itself is decreasing. An plus 1 less than equal to an, and limit an goes to 0. And then we have to have these two conditions, then it converges. Well, we can, if we use this theorem, you can say this one, yeah, it converges, because first n goes to infinity, 1 over infinity goes to 0. We also can compare 1 over n plus 1 less than equal to 1 over n. If I use this theorem to do this, first limit n goes to infinity, 1 over n equals 0. That's right. Second, okay, so 1 over n plus 1 less than, well, not like equal to, just less than 1 over n. Okay, perfect. These two conditions are met, and then this will converge, right? Well, so now I want to tell you why this one, why do we have this theorem? Why does this one converge? Let's look at the proofs real quick. I want to tell you why. Consider have n from 1 to infinity, -1 to power n plus 1 an. So this one gives us S2n equals a1 minus a2 plus a3, if you have that, right? S means summation, the first two n terms. a1 minus a2 plus a3 minus a4 plus a5 minus a6. You know that because our signs will alternate, right? Okay, so if I combine two together, so I get S2n equals a1 minus a2 plus a3 minus a4 plus a5 minus a6, plus add all of them together. Okay, so I'm going to look at this S2 and this series. Okay, basically I will have S2n equal S2, sorry, if you look at the series of this one, so you get S2 equals a1 minus a2, S4 equals a1 minus a2 plus a3 minus a4. That makes sense to you, right? And then S6 equals a1 minus a2 plus a3 minus a4 plus a5 minus a6 for 6 terms. Okay, so if I continue, I'm going to have S2n sequence, S2n, like that. S2n equals 2n terms, a1 minus a2 plus a3 minus a4 plus, continue, plus a2n minus 1 minus a2n, right? That's 2n. Alright, so if I write down this, what I can do, I can write S2n equals A1 minus A2 plus A3 minus A4 plus A2n minus 1 minus A2n. Okay, so if I combine these two together, I put a negative sign here, then I must change the positive into negative here. Minus A4 minus A5. Okay, and you have last two is going to be an2n minus 1 minus an minus 1 and minus a2n. My question is, from the second term, from the second condition, an plus 1 is less than or equal to an. So my question is a2 minus a3 positive or negative? Okay, an bigger than or equal to an plus 1. So now I want to ask you, Nicholas, could you please tell me if this one is bigger than or equal to 0, less than or equal to 0? Very good. It's greater than or equal to 0. Perfect. Okay. So this is greater than or equal to 0. Okay. Now a1 minus a number, all of them greater than or equal to 0. All of them greater than or equal to 0. All of them greater than or equal to 0. If a1 minus all of these numbers, now I want you to compare S2n and a1. Or maybe just the S. Yeah, just S2n. Yeah, S2n and A1. So now I'm going to ask another student, can you tell me S2n and A1, which one is it less than equal to or bigger than equal to? Thea, could you please tell me? The question is S2n less than equal to or bigger than equal to A1? S2n is A1 minus a lot of things. So basically, less than equal to. Very good. Okay. S2n is greater than equal to A1. So which means S2n is a bounded series. S2n is bounded. And S2n is long decreasing. Because you look at this, okay, they're all long decreasing. So S2n will converge. I just give you that brief introduction. We're going to continue tomorrow. Okay, I will tell you long decreasing sequence, bounded long decreasing sequence converge, right? All right, so we're going to continue tomorrow and finish this and see more example of alternating series. All right, thank you very much.